So give me a little bit of an overview of your rocket and what's your altitude, what's your payload?
All right. Rochelle, do you want to take that?
Yeah. So our goal was to compete in the 30,000-foot altitude with a student researched and developed motor. A lot of our rocket was student researched and developed. And then we were able to compete June 5th at the Friends of Amateur Rocketry site in the Mojave Desert. We reached an altitude of 31,042 feet and were able to successfully recover our rocket.
Good, okay. What kind of payload do you have?
Yeah.
Or are you planning, I should say?
We already did it. It was a rover payload.
Oh, okay, yeah, sorry. I'm in Ezra mode, so I'm fast forwarding to 2022. I got you. So your payload was a rover?
Mm-hmm.
Okay. Okay, very good. What led you to that decision to that kind of a payload?
We have Jeremiah Washington here, who is our payload lead. Jeremiah, would you like to take that one?
Sure. So the inspiration for the choosing a rover was actually due to the proximity to the Trinity test site just north of Spaceport America, which is, I think, within like about 90 miles. So we wanted to see if we can create essentially a hazmat or CBRN, which stands for chemical, biological, radioactive, nuclear, and explosive support rover to drive around and see if we can detect anything. Not that we expect any high amounts of radiation, but we did have a Geiger counter on board and air volatility sensor, and a few other sensors to measure out like the bio readings of the area.
Mm-hmm. Okay, very good.
Yeah, I'd like to ask something for your recovery specialist. You did a quick scan through your video and noticed that your main deployed at apogee in your test flight. Can you talk about that a little bit and what you've done to make sure that it doesn't happen again?
Yeah, so on our test flight, the main deployed at apogee, and we noticed our rover actually deployed at apogee as well. So when that came off the lead screw and made impact in the nose cone, that was enough to break the shear pins. And eventually the main parachute came out as well. Looking at the flight computer data, the flight computer did not trigger at apogee. The flight computer triggered around 1,500 feet, so we know that it wasn't a trigger from that, but it happened because our payload got deployed early. And that, looking back at all the data and stuff, we can attribute that to the not flight computer. We had another Raspberry Pi inside our rocket. It was actually in the rover compartment, and that overheated a little bit, causing it to turn off, which turned off the power to the lead screw. And so the force of the rover just pulling on the lead screw caused it to unwind, and the rover deployed that way. So going forward, we would put in more vent holes, and we did turn on our rover a little bit early, a little bit earlier than we would have liked. So everything heated up from that. So going forward, add more vent holes and make sure we don't turn our electronics on too early.
Okay. Well, so then that leads me to a second question. Since you had separation due to the rover moving around, how is your black powder configured to make sure that it actually works at 30,000 feet? Because that's always an issue.
So for our black powder, we had little copper caps, and then we 3D printed inserts so that the black powder could be tightly packed in there with the correct amount, and made it kind of a cannon, charge cannon, so that way the everything can combust accordingly with the oxygen that's available up at 30,000 feet.
Okay, and so okay, and so did the charges actually fire at 30,000 feet, or did they? There was the only place where the flight computer fired the charges was at 1,500 feet.
The drogue charges did fire at 30,000 feet. So the drogue parachute came out
Okay.
perfectly fine, and then when the payload came loose, that caused the shear pins to break on the main, and so then the main deployed with no charges actually having gone off.
Okay.
I see what you're saying. Yeah. Okay. Mhm.
So after nose over, the payload fell out of its housing and carried enough force to fall into the nose cone, which sheared those shear pins and deployed the main.
Yeah. Yeah. I see you guys had to walk nearly 6 miles out there. So that's a pretty long walk on a hot day. And, you know, out here at the spaceport, it'll be even hotter. And with the New Mexico winds would be a longer walk. So that's something that you really need to concentrate on.
Yeah, we were lucky that it landed near a road, so we were able to drive within half a mile.
Oh, super lucky.
Yeah, yeah, no kidding. Yeah.
Hmm.
So for anybody here, you know, what is it about your project on the day before launch that's going to keep you awake all night?
Honestly, for me, it was nothing because we showed up at the launch site the Friday before, June 4th, and we launched on June 5th. We had everything set up for our safety and pre-flight inspection. Everything went really well. The guys at FAR had us put together our rockets so that they could see that we knew how to do it, and we did. And then they had us take it apart in front of them and explain how everything worked. Everything went really well. They asked us a few questions, gave us a few tips. But we were able to finish all of that stuff pretty early and, you know, have a few hamburgers and go to bed.
That's pretty good. If you can have hamburgers.
Okay, well, that's always a good sign. Yeah.
Yeah, for sure. So you develop your own motor for this. What led you down that road, and what are some of the different types that you considered in terms of options for making your own propellant?
Sure. So Cal Poly Pomona does have a pretty good history of making our own motors. We started doing this about 4 or 5 years ago. And so we're continuing that heritage of making our own propellant, machining all of our own motor hardware, and making a O-class motor to compete in a 30K competition. We competed in Spaceport in 2017, and then the last 2 years we competed at FAR, and now we're back at Spaceport. We used to use MIT Cherry Limeade, but due to its packability instead of pourability, we noticed there was a significantly higher range in performance variation. So we decided to move to a pourable formula called Reliant Robin. This one also led to a much higher ISP. It was because we were running at 12% metals instead of 8% metals. So the only concern for this propellant was heat, but we were able to thicken our liners. We used Franklin XX phenolic liners at 1/8 inch thick, and we did 2 static fires, and those liners were absolutely perfect throughout the entire burn. And it was a long burn as well, 7.5 second burn to 7.6 second burn. We had 2 successful static fires and then moved to a perfect flight.
Nice. Okay.
Can I ask a question?
Sure.
So I jumped in a little bit late. I apologize. Kind of filling in. So is this a completely solid, or is this a hybrid? You said it was a Class O.
So Class O stands just as the impulse amount.
Sure.
So this is a 95% O that is completely solid.
Okay, it's completely solid.
Mhm.
And then, so for you said you use phenolic liners. What's the actual case for your motor?
It is a 6061 T6 quarter wall aluminum casing.
Aluminum. Okay, so you just have the phenolic directly in the aluminum, and then you make your mix and then pour it in.
So we actually put our mix, we have a 5-grain structure. We mix our propellant and cast it into casting tubes. And then those casting tubes have a mandrel in them since we're doing Bates grains. And then all 5 grains then get stacked up and then bonded into our 1-piece liner. And then we grease up the liner and slide the liner into the aluminum casing.
And are the casting tubes part of it, or do you pull them out of the casting tubes?
The casting tubes are part of it.
Okay, so is it 5 stacked? So you do like short stacks of 5?
Mm-hmm.
Okay, and then do you mandrel them after you have them stacked?
So they're
Each individual.
We mandrel each individual one because there's varying core sizes.
Sure, that makes sense.
Yeah,
sure.
and then we do that so that we can have the faces burn.
And do you tumble them before you mandrel them, or is it just a straight pour? How are you pouring them solid and then doing a full mandrel, or do you have?
Oh, so our mix before it is cured is fairly liquid. It's so we have a little dish that we put our casting tube in and our mandrel in, and then we can pour right from our mixing bowl into that into the shape of our grain, and then it cures in that shape. Of course, we'll vacuum it first to get all the air out, and then we pour into that shape, and then we'll have 5 grains, each with the mandrel pulled out. So it'll be 5 Bates grains, very similar to like putting together a Aerotech RMS motor.
Okay.
You just get those grains in the mail. That's what we end up with, and then we stack them up and then it's the same thing with Aerotech gluing. It's the same process to glue in Aerotech grains that it is to glue our grains into the liner. You would glue grains into the liner, slide the liner over, and then you would grease up the liner and slide the liner into the casing, and then put your bulkhead and nozzle in on either side, and then bolts.
Great, thank you.
Very good, thank you. And that puts us right at time, actually. Any last thoughts? Okay, thanks very much, team.